couple of word problems. Ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet, using the fact that the acceleration due to gravity is 32 feet per second squared. Find the position function given the height s as a function of time t. So we're starting off with acceleration as 32 feet per second squared. Right. Now, direction is going to be an important thing here because acceleration due to gravity is a downward motion. So we'll put a negative sign there. So when I want to integrate, or at least go through the process to develop the solution, which will require integration, I want to keep track of little details like that. All right, so this is something that could be written as d of a of t dt is equal to negative 32 feet per second squared. All right, so that's the differential equation. But if we put it in differential form, now I'm looking at this whole thing with a dt at the end. Oops, we lost part of my equal sign. Okay, so I'm going to integrate both sides. Now the thing that's going to make this different from what we were doing previously is it's regardless of how complicated the units make it look, it's still constant. All right, so it's something we could take the antiderivative of. We have an understood one here. The antiderivative of 1 is the variable. The variable is a of t. So a of t all right, so apologies. Can't get out of my own way sometimes. It's a of t is the derivative of velocity. So these should be v's. So the antiderivative of the negative 32 is going to be negative 32t plus some constant c. All right, now the units are going to be feet per second. Because if we take feet per second squared and multiply it by some change in time, which would be measured in seconds, right? Feet per second squared times seconds is going to be feet per second. All right, I'm actually going to write this as seconds because I just realized since we are talking about position, we're going to incorporate the variable s. And that's going to get confusing. And since I already made one mistake, I don't want to get to a point where I'm confusing the living daylights out of people. I'll confuse you a little. Confusing you a lot is unacceptable. Okay, so oops. Gotta get back on track here. So there we go. So we have this relation. V of t is equal to that, all that good stuff. So now they tell us, or maybe they had always told us, that the initial velocity was 64 feet per second. So that's the velocity at time t equals 0. So v of 0, negative 32 times 0 plus c, feet per second, is equal to 64 feet per second. So we're going to have c feet per second equal to 64 feet per second, so therefore c is the number c is equal to 64. All right, so we have our starting value, which is great. So, the question I normally get at this point is, well, couldn't we just put the initial velocity in for c and call it a day? Well, you're not always going to be given an initial condition. You'll be given a condition. It won't always be the starting value. Right? You might have to solve for the initial value. Right? So we can't make that assumption. Long story short. So v of t is equal to negative 32t plus 64 feet per second. All right. So now what I need to get is the antiderivative of that. All right. So the antiderivative of v of t. All right. So that's what we're looking for, but kind of run into a little bit of a notation, sort of an issue. Maybe it's not an issue, but it's really more like just a fact that you need to know. Right? S of t is equal to the antiderivative of v of t. All right. So that's the fact that we need to know. All right. So we can apply that, which is ultimately the plan. All right. We could also say things like, ds dt is equal to v. That's a consequence of this. It's a relation that emerges from it. These are all things that come into play. So I could just jot them all down at the top here so that you have them. We start off with ds dt is equal to v, dv dt is equal to a. Then we start working backwards. We say the antiderivative of a with respect to t is equal to v. And we say the antiderivative of v with respect to t is equal to s. There's a bunch of different ways of representing it all. So, and then what we did previously, which is to say that the derivative of the velocity function is the same as acceleration. So if we have it in differential form, so I'll take this whole shebang over here and replace through a little basic substitution. I'm replacing this with d of s of t dt. So it's just another layer of the notation that's coming into play here. It's in a lot of ways it's the notation that kind of gets people confused, but I can and will say that the notation is going to end up being probably the most important part of all of this, because most of the time, you think back to Calc 1, well, like you have no idea what you're doing, but you do know that at some point you're going to take the derivative, set it equal to 0, and solve. It's like, okay, great, but why are we doing that? It's kind of along those same lines here. We got to get at the heart of why we're doing the things that we're doing. So ds dt is going to be equal to the whole right-hand side. Which in turn is going to lead to the next step in the process, which is basically going to boil down to the dt getting smidged over to the other side, and then we integrate both sides. Right, so the 1 becomes a ds, I'm sorry, becomes a s of t. The units associated with time again are seconds, or is seconds. So we have a nice little cancellation of the units here, of time, essentially. Antiderivative of negative 32t is going to be negative 16t squared plus 64t plus c feet. Now they told us that the initial height is 80. So s of 0 is plugging in a 0 everywhere I see a t is going to give us an 80 for the c value. So 80 feet is going to be equal to c feet, which means c is equal to 80. Which gives us the position function for this situation as negative 16t squared plus 64t plus 80. Alright, so then everything after that is just algebra. It's like, when does the ball hit the ground? Well, that would be when the height is equal to 0. And you could solve that any way you like. Alright, you could use a graphing calculator if you want. So y equals, pop in your function negative 16 x squared plus 64x plus 80. And just take a look at the picture. I mean, start off with that. It looks like maybe not the cleanest intersection. It's hard to tell though. Alright. So, what we can do, you could use the 0 function, but I prefer to find the intersection. So what I'll do is I'll put the 0 in as a second equation, go to the graph. Actually, let me make that bold so it really pops out. Alright, don't care about the negative one, that'll be back in time. Care about this one. So second, trace 5. The first curve is the parabola, second curve is the horizontal line, and then I would just right arrow until I'm closer to the intersection I want than I am to the intersection I don't want, in which case it spits out the intersection, which actually is 5. I guess there's something wrong with the something off with my tick marks. So t equals 5 seconds. Alright, so let's see. Oh yeah, my x scale is based on a trig problem I was working on at some point. So I'll go negative 10 to 10. Go by ones. Yeah, a little clearer. Or you can go Desmos, type in your equation, you could use x's, you could use whatever you like. If you're using a graphing approach, obviously the x's, but if you're using a numerical approach, you can see, or you can use other methods. Right, so just type it in. It's a little cleaner on Desmos. I mean by a little, I mean a lot. So you just click on the x-intercept. It presents it as a gray point first, and then you click on it, it gives you actual coordinates. So that's probably the nicest way to do it. All right, you could also do it algebraically if you want, but I'm not requiring that. So that ends up being a choice that you would make yourself. All right, number 5, the elevator in a building passes the 50th floor with a velocity of negative 8 meters per second and an acceleration of, well, it's a linear equation. And this linear equation can be cleaned up so that it's power rule ready. Each floor spans a height of 6 meters. Find out which floor the elevator will stop. All right, so we know A of t all right, we could also figure out V of t by taking the antiderivative. We can sort of cut out some of the fluff here now. It was really, the last problem, I did it in painstaking detail, just to kind of get at the underlying concepts. But now it's like, okay, well, we don't want to have to beat it to death every time. So we just kind of jump right to, jump to the chase, or I forget what the expression is. Anyway, increase the exponent by 1, divide by the new exponent, so 1/18 t squared minus 5/9 t plus c. All right, they say that we have, once it passes the 50th floor, it'll have a velocity of negative 8 meters per second. So let's call that time t equals 0. They didn't give us a starting time, so maybe we're the ones on the 50th floor. I mean, we only care about what happens in relation to the 50th floor. We don't have anything else to go on, so why not just let that be the moment that time is equal to 0? Right, in which case it'll be pretty easy to figure out the c value, because then I can replace all my t's with zeros. So we would end up with c equals negative 8. Right, so v of t is going to be equal to all of this stuff with minus an 8 at the end. All right, now we also need to, ultimately we need to find out which floor the elevator is going to stop, but they do give us a measure of height, so ultimately we're going to need to figure out the position function. So s of t is the antiderivative of velocity, so let's grab our velocity equation, expression. So increase the exponent by 1, divide by the new exponent, so 1 over 54 t cubed minus 5 over 18 t squared minus 8t plus c. That's my s of t. All right, now they're telling us that each floor spans a height of 6 meters. The 50th floor would then be 300 meters up. All right, at time t equals 0. So s of 0, 1 over 54 times 0 cubed minus 5/18 times 0 squared minus 8 times 0 plus c. That's going to result in a 300 equal to c. So we can now say that our position function is all of this stuff plus 300. All right, so that's good news. So we have velocity model, we have a position model. Find at which floor the elevator would stop. Well, it's going to stop when its velocity is equal to 0. All right, so I'm going to solve this equation for when the velocity is equal to 0. I'm going to use Desmos. So let's put an equation y equals 1 over 18 x squared. Oh, that's not an x squared. I'm panicking. X squared minus 5/9 x minus 8. All right, so And the reason why I want to use this technique is because it's just going to be so much easier to figure out the roots. All you got to do is click on it. All right? So this happens when t is equal to -8 or 18. All right, so just got to remind myself of what the question's asking. Find out which floor the elevator will stop, so it's a moment in the future. And it's all I care about is the 18. So then what I would want to do is evaluate my position function for the 18. So more typing. But what I'll do here is I'll put this in as a function of x. 1 over 54 x cubed minus 5 over 18 x squared minus 8x plus 300. All right, so then I'll just evaluate this by typing in f of 18, and it appears to be 174. So that's 174 meters. They said find which floor, all right, which floor it's going to stop. There's 6 meters per floor, so it will be the 29th floor up. Or I'll just say 29th floor, because we don't want to get too crazy here. What we're going to end up with is kind of the particulars about a building, like is the first floor actually the first floor, or is it like the lobby and then floor 0? And like how's it structured in this particular building? We don't know, but what we'll do is we'll just assume that it's the 29th floor and call it at that point.